In this video, I will be talking to you about thread synchronization. So imagine you have this class. It has a local variable, actually an attribute, sorry, that is initialized to 0. And we have an accessor to this attribute, a public or package accessor in this case, called score, that takes in a certain value and adds it to the score. However, to make this addition a bit more dramatic, so we are copying the value to temp. We are adding the value v to temp, and then we are putting back temp to score. I agree with you that usually you would have done something like score plus equal v. And it happens that this instruction is kind of atomic in most programming languages, particularly in Java. Although in assembly code, this would have been translated into load the value of the variable up, the variable called score from the RAM into a certain register, let's say R1 within the CPU, then load the value of V into another register, because CPU cannot make an addition directly in the RAM. They can only sum up registers. So now we can call the add instruction to sum up in R3, R1, and R2, and then store the value of R3 at the address of score back. So in assembly, it's even more than it's almost 3 different instructions. Okay, so 4 different instructions. So suppose that after loading those 2 different values, the first thread has been interrupted here. Okay, so the values that are loaded at a certain moment, suppose we load 0 and we load the value 1 from thread 1. But then if thread 2 is willing to store in score the value 2, we expect that at the end we have the final value equal to 3. But surprisingly, if the first thread is interrupted here, the second thread would read the same value from the RAM, the same original value, which is still 0, and will store in V, a different copy of V, the value of 2. And now when the execution resumes on the first thread, we would find that R1 is equal to 0, R2 is equal to 1. This will sums up to 1, which will, maybe we won't have the time to save back in score, suppose. Okay, so thread 1 is interrupted here. If a thread 2 is asked to execute at this moment, then don't forget that the original values of score and V were equal to 0 and 2. So here the summation would sums up 0 and 2 together. And imagine that thread 2 stores this value back in a score. So we will find out that score is equal to 2 at that moment. But if thread 1 resumes its execution and resumes with this instruction, it will store 1 instead, because the final result that thread 1 got is equal to 1. So very surprising, very disappointing, but this is what happened actually when you have multi-threading and you have 2 different threads accessing the same shared resource. So the assumption that we're making here is that each thread is accessing the same instance of scorekeeper. If each thread has its own scorekeeper copy, this won't cause any problem. So again, if a thread calls score1 and another calls score2, we will end up having an erroneous result. To accentuate this effect, I have prepared a piece of code with this keeper class. So the file is called synchro example. In the main, I'm creating an instance of my synchro example, and I'm calling the function launch, which is actually creating one single score keeper, and it's passing it to each score incrementer. The score incrementers, I have created an array. Well, I only have two because it's sufficient to see the effect, but you can create more than two different score incrementers. I'm passing this score keeper to the constructor. Let's see what those score incrementers do. So they keep this instance here in a private attribute, and in the run function, they call scorekeeper.score1 for 100 times. So they are just increasing the score by 100 times. So we're expecting, or we should be expecting, that with two score incrementers, we will get the sum to 100. How to call them just technically, because we haven't seen such code. I'm looking over those score incrementers. I'm initializing them with the same score keeper once again, and I'm starting each one of them, one after the other, very quickly. But then in another loop, I'm joining every single one of them. It's important to join in a separate loop, because if you join within the same loop, after each iteration, you would create one incrementer and then join it until it finishes, and then you will create the second one and ask it to start, and then join it, and so on and so forth. No, I want to start. I want all of them to start, and then I will join all of them in a subsequent for loop. When I finish, I would display the final score from the score keeper. So I added this gather method to get the score. Okay, so surprisingly, Java does very well here, because those instructions are usually non-interrupted. When you call the score function, it happens that Java rarely interrupt this function. So if you run your code, you rarely get an erroneous result. So well, we were lucky to have an erroneous result, but usually, most probably, you will have 200 displayed clearly on your screen tens of times before you get an erroneous result. So each time I'm running my file, so good, we have another one here. Okay, so just to let you know that we do not have any guarantee on the output. Okay, so cool, it's already giving us what we want, but just in case it is not, it's systematically giving you 200. What you can do is that you can add a few output instructions. So once again, I have also added one here between these two different instructions, just to accentuate this effect. Okay, and now absolutely we will have certain delays, because while outputting, this takes a lot of time to output on a certain output stream. So so here we have only 116 as a final result. So just to, or maybe you can add a certain sleep function here, just to accentuate this effect of doing a certain sequence of instructions that should have been done in an atomic way. Nevertheless, they have been done um, in parallel with a race condition between the multiple threads. Okay, good. So you will have this code on GitHub to try it out, and I hope that with this example, you get a feeling of what does it mean to synchronize threads. So we need to synchronize them so that when they perform this, when they call this function here, when they perform this action, they do it atomically. Okay. Okay, and we also want this section to be considered as a critical section. So a critical section is a section of code that we want only one thread to access it, only one, or at least in certain problems, at max n threads within that section. Okay, in our case, n is must be equal to 1, so we should allow only one thread to run this code at a certain moment, because if two different threads read two different values for this core and then make two different additions afterwards, they will override the work of each other. So how to do this, how to synchronize the threads. So I think we have a much more in-depth discussion of synchronization of threads in the theoretical part that we skipped for the moment, but we will get back to it. In Java, each object can be locked actually. It has a lock that may be owned by at least one thread. How to do so? So the thread can call synchronize, can ask the Java runtime environment to synchronize its work based on the lock of any object that you have in hand. So maybe you have the scorekeeper object, okay, in hand, and then you call synchronize on the scorekeeper. You call scorekeeper dot score. I forgot the name of the function, so maybe yeah, it's score, and you pass 1 to it, okay, and then you release the lock. So implicitly here you get the lock over this variable, and then here you release, I mean the thread that is calling this code releases the lock at this phase. So as if we surrounded the score function with a critical section with a lock access. So usually a thread waits if it attempts to obtain an already obtained lock. So any thread, like if the first thread calls this function, will lock this variable and do whatever it wants with it, and then release it at the end. If before releasing the lock another thread comes, well, it must join the first thread until it finishes. So it cannot run anything else because it's really waiting. It's willing to access this line of code. This is the logic of the sequential code that is calling. So it must obtain the lock first. So it will wait here until the first thread continues the execution until the close the braces, and then it releases the lock. And when it's released, only at that moment thread 2 can get in and continue the execution. The lock is typically a counter, so one thread may lock an object more than once. Each time it's locked, no other threads will come in, and then once the lock has been released, another thread can take it. So this is why we can call this synchronized block and pass any variable to it, as I told you before, calling a function in it. So a synchronized statement waits for obtaining an object's lock before running its body, and then it releases the lock when the body terminates at this close the braces. So it's obtained there and it's released there. So obtain the lock and release the lock here. The choice of the object to lock is by convention, so it's up to you. Usually it's the object on which you have a race condition or on its one of its functions. By the way, we can also define synchronized methods. So without getting a lock on the original object, we can get normal access on the object. But in its definition, we can make any function synchronized. In this case, the synchronized attribute is equivalent to enclosing the body with synchronized on this. Okay, but just bear in mind that if you have two different atomic counters, one that is shared between those 3 threads and another atomic counter shared by only 2 different threads here. So this one will have an independent run from that one. Okay, so only one of these 3 threads will be able to access this atomic counter, and only one of these 2 threads will be able to access the inner counter. So and really it's up to you to define the logic of your application and to know on which object you want to wait, and so on and so forth. And besides it, if this thread is accessing the method count, maybe if this thread is doing count, okay, and if you have another function called uncount, let's say, nothing prevent those two ones from calling uncount, okay, unless they are waiting on count, so they can call uncount at the same time. And in case uncount also changes the same variable count, okay, well, in this case, this synchronized call is not sufficient because it prevents the others from calling count, but it does not prevent them from calling uncount. Okay, so we may have another one calling uncount, and even both of them calling uncount and working on each other feed. Okay, so if you have multiple functions that also have coding common, but they have different name, well, then in this case, the only way out is to call synchronized on the object itself, on the counter itself as a whole, on the atomic counter. So it's nevertheless, if it's only one method, then the most common way to achieve object level atomic operations is to use synchronized on the function right away. Once again, only works if, okay, this function is independent of any other function inside the same class, and then the implementation guarantees that at most one thread can run a synchronized method on a particular object at once. Once again, nothing prevents them from accessing another method, whether it's synchronized or not, okay? But we have to be careful. We will discuss multiple properties of parallel algorithm later on. One of the nice properties to have is to avoid any deadlock and to guarantee the liveness of the parallel code that we are writing. So suppose you have two different threads and you get stuck into a certain piece of logic where you want to get the lock over foo, then over bar to do something. But thread 2 gets a lock over bar, then over foo to do something. The problem is, once foo is locked, let's say the execution happens in this manner. So thread 1 executes this instruction first, then thread 2, then it's interrupted, and a thread 2 gets the runtime, so it executes this one at the second time. So now bar is locked. Well, even if thread 1 wakes up and tries to get the lock over bar, well, it's too late because bar has been already locked by thread 2. And even if thread 2 wakes up or continues executing this line of code, well, it will be soon blocked over foo because foo has been already locked there. So no matter how you execute 3 or 4 at those two different lines, it's too late. They will be blocked and blocked forever. This is what we call a deadlock. Okay, so the rule, always acquire locks in the same order. Okay, do not reinvent the wheels and imagine cases where you need to do it in this different order. But of course, in a complex code, we may get easily lost and we may lose control over the code. This is why we have to run it and run it in extreme conditions and in order to make sure that it really yields the expected results. Okay, so more about deadlocks and synchronization will be given later on in this course, but at least now you know about this synchronized control structure that prevents two different threads from accessing the same object, any function from that object, and it can be downsized to only one function if it is the only critical section, or if it is a separately critical from other functions, whether they are synchronized or not. Okay, so that's it for this part. I hope you can prepare them before next session on Friday. See you soon.